Okay, now Pascal's principle is the principle behind hydraulic lifts and what have you. And it just says that a change in pressure is felt at every point in an incompressible fluid. Now, fluids, when we use that term, a fluid refers to anything that flows. And so fluids, if we think about our states of matter, are comprised of liquids and then also gases, because gases also flow. Now, gases are compressible. So Pascal's principle does not apply to gases. Virtually all fluids are incompressible. All right, that means that if you apply a pressure to them, they don't change shape. Or they change shape, but they don't change volume. All right, so you can't compress them down like you can a gas. And that's just because of the structure. So virtually all liquids are basically incompressible. And so for all liquids, then Pascal's principle will hold true. And Pascal's principle just says that if I apply a certain pressure, let's say I have this liquid inside a piston, and I apply a certain pressure, I apply a certain force over the area of this piston, then that's going to cause a change in pressure in the fluid. And that change in pressure, that same change in pressure, is going to be felt throughout on all sides of the container and within all points within the fluid. All throughout that fluid, that change in pressure will be experienced at the same level, at the same magnitude. Now, this makes for a nice application in hydraulic lifts, or hydraulic systems of all kinds. We actually have hydraulic systems in a number of different mechanical devices. For example, in a car lift, like here, if you've ever been to a shop and you lifted your car up on a jack, many of the jacks that you have in your car, some of them are based on a screw type mechanism, but others are actually hydraulic lifts where you have a couple of different sized pistons that allow you to lift the huge mass of your car. You also have hydraulic systems within your car that operate your brake system, where you push on your brake pedal. That applies a pressure to a piston that's small, and then this subsequently provides a pressure to a larger piston that actually engages your brake pads onto the rotor inside your wheel or behind your wheel. But this is a hydraulic lift. In the hydraulic lift, the input pressure is equal to the output pressure. That's Pascal's principle. If I have a pressure that I apply to a liquid, then it's felt all throughout that incompressible liquid. So here, I apply a pressure at this point, and then I get the same pressure out. And so a hydraulic lift exploits Pascal's principle and changes the size of the input and output pistons. All right. So I know that Pn has to equal P out. Right, that is that F1 over A1 equals F2 over A2. So if I change the cross-sectional areas of the pistons, like I have in this figure, where A1 is really small and A2 is relatively very large, then I'm going to get a much larger force. Say, for example, I have 100 newtons of force over here, and I have an area of, say, 0.01 square meters. And over here, let's say that my area is 1 square meter. Then what force do I get out? Well, I can say 100 newtons over 0.01 is equal to F2 over 1 square meter. So this is going to be 10,000 newtons is the force that I get out for F2. So I put in 100 newtons and I get out 10,000 newtons. Now you might be saying, well, wait a minute, this seems to violate the conservation of energy, because it seems like I'm putting in 100 newtons and I'm getting out 10,000 newtons. So aren't I in some way creating some new energy that isn't accounted for? I'm doing a certain amount of work on one side and seem to be getting more work out on the other side. All right, that's not the case though. Let me erase some of this. Because if you recall, work is the product of the force times the displacement. All right, work equals force times displacement. So I have a small force over here, but I have a big displacement. So that means that I'm going to have to move this piston to a very large displacement in order to move this piston just a very small amount, say up to that point. All right, because over here I get a big force, but a very small displacement. So the work done here is equal to the work done over here. We talk about this in terms of mechanical advantage, that while you're still doing the amount of work required, you get this mechanical advantage. You can see this in hydraulic floor lifts, like the floor jacks, if you have one that you use to lift your car. You have to move, you have a jack that looks something like this. It's usually on wheels. And you have this thing right here. And you have to move this handle up and down in order to make this go up. But each time you move it up and down, you have to move it up a very large distance just to make the jack just go a very small amount. And so that's here as well. And so, in fact, energy is conserved in hydraulic systems. So everybody can rest. It's okay.